My name is Dripto. I'm a research scientist on the quantum AI team at Google. And I'll be talking about this result that, well, this archive posting is a bit out of date now, but that we put in on Nature, I guess Monday, along with our Willow result. So this talk will be in the context of this error correction experiment, but also start talking about some of the improvements we've made to our chip and processor along the way to get better performance. Oh, sorry. Great, cool. So quickly, let's just talk about quantum error correction. Well, right now, our devices have about a 10 to the minus 2, 10 to the minus 4 error rate per operation. And for most of the practical applications that we talk about in conferences like this, we're really considering computers that exist more in this 10 to the minus 10 and beyond range. So to bridge this gap, we use error correction. I'm not going to cover that in too much detail in this in this context, but the way we do that at Google is using the surface code. So we build a square patch of qubits, and we have a checkerboard of stabilizers of types X and Z, and we use these measure qubits in blue to measure the eigenvalues of the operators that surround them. And the overall goal is that as you build these error correction systems and you make them bigger, you can have them perform better, as long as you're below some critical point. So to see that, we can look at this sort of purely theory plot here on the right, and talk about a few of the different numbers that we're going to really discuss in this talk. So first, I'll mention that on the x-axis here, we have the physical error rate of our device. Here we're showing the 2-qubit gate error rate, but we're using SI1000 noise, which is a single parameter noise family that basically gives you measurement error, single qubit gate error, and so on as multiples of this single parameter. And on the y-axis, we have the logical error rate per cycle. So how much logical error do you pick up on one round of syndrome extraction? So what you can see for these different color lines or different distances is that there's this critical point called the threshold where they start crossing over. And so above the threshold, smaller distance codes perform better, and below the threshold, larger distance codes perform better. And crucially, as you get below the threshold, you can start arbitrarily increasing your distance to get lower and lower logical error rates. And the factor that you pick up is lambda. So that's shown here in this equation, where lambda, or 1 over lambda in this case, is really the key metric that we use to decide how well we're doing error correction-wise. The reason this is nicer than logical error rate for us is that it's an intrinsic quantity, so it does not change as you look at your system sizes. And you can really think about this as being a simple function of the error density in your device. So error correction is a path towards low error rates, but only if your hardware is good enough. And this demonstration is us sort of unequivocally showing that we are now beyond this point. We're farther to the left here, and we're now starting to have non-trivial behavior as we scale our devices. Cool. All right, so in this paper, we're going to discuss 3 sizes of the surface code. As I mentioned earlier, they're just larger squares with the same general idea. So we have a distance 3 surface code. Here on the bottom, it tells you how many errors it can handle at a given time. And so a distance 3 code can only guarantee that you can fix any single error. There are 2 error patterns that will fool it. Similarly, for distance 5, you get any 2 errors for sure, but 3 and more, you might have issues, and so on for distance 7. And on the bottom, you can see the number of qubits. The number of qubits is 2d squared minus 1. So we are increasing the number of qubits, and we're adding overhead, and hopefully we can pay that overhead off. Great. So let's get at, oh, no, my surprise. Yeah, great. So here I'm going to talk about first the data we showed in 2022. So here we have 2 plots that are overlapping, the distance 3 and distance 5 error rates, where logical error rate is now on the y-axis, and the x-axis is the number of rounds we've done this, so we've repeated it over and over again. And the key thing to see here is, well, there's 2 things. One, as my now ruined surprise shows, there's a lot of white space here, and that might give you a hint as where we're going next. And 2, these 2 numbers were basically on, or these 2 curves are basically on top of each other. So we were reaching the break-even point, at least the 3.5 break-even point, but we were not yet at a place where increasing the distance was really worthwhile for us. However, with our new Willow chip, we are pretty comfortably at the point now where the larger distances, which are shown in the darker blue here, lighter blue, are far better than the red distance 3 chip. So there's some details here in terms of like which exact footprints we looked at. Roughly speaking, we tried to keep things pretty even so that no one qubit was overrepresented and could skew results. And the key point here on the right is that we now have these 3 like logical error points for distance 3, distance 5, and distance 7, and they fit a line. And that means that we're starting to see the sort of promised behavior of the very clean theory, where as you increase distance, you pick up factors of lambda, and the same factor picks up each time. Great. In general, as we've talked about in Willow, we have better physical qubit gate times. We have better T1s. This corresponds to about a 2x lower physical error rate. And then, as I'll discuss more later on, that corresponds to a 20x improvement in logical error rate. And that's because as you increase the distance of your codes, you're more and more sensitive to improvements in your error rate. So yeah, there's a bunch of data here if you're interested. And this gives you a sense of sort of error density for the previous experiment. Sorry, I'm having a bit of issue with this clicker. Great. Oh. Sorry, over-click. All right. Great. So just to look at sort of how these two error distributions compare. It's kind of harder to see in this horizontal picture, but the error distributions for our new device have shifted to the left, roughly by a factor of 2.2. The biggest improvement is in T1, which went from 20 microseconds to 70. And in terms of detection event fraction, which is not shown in this one, but is shown here, it went from 18.5 to 8.5. So the detection event fraction is the likelihood that a given measurement flips in the next round. Gives you a sense of how many errors there are in your device sort of holistically. And in the bulk, we had about a halving of this parameter. And on the right here, you can see, because we have distance 7 codes and in the largest instance, it takes 4 errors for us to have our experiment fail. And that means that you're quintically or quartically sensitive to improvements in your logical error, or in your physical error rate. So that's where this 20x improvement comes from just a 2x improvement at the physical level. So in the next few slides, I'm going to hopefully talk about some of the improvements we made to actually get there. The first one I'm going to talk about is resistance to these error bursts. So we also use repetition codes in all of these surface code examples or experiments. And the reason we use repetition codes is they're a much easier code to actually implement. They have a much higher threshold, they're much simpler, and they allow us to forecast sort of problems that are coming along down the line. And so back in 2022, we ran this experiment, and you can see the surface codes up here were basically the same, but the repetition code for that same chip were dramatically improving in performance as distance increased. However, there was this sort of leveling off, this floor here, and that was due to a single high energy event. So if we removed 0.15% of our data, you ended up seeing this floor go away. But in a real experiment, we can't remove 0.15% of our data. You need to use every shot. And so we needed to fix this particular issue. And what it looked like was these high energy events that you can sort of see here. Here, this is the T1 of our device over time. And randomly, you'd see these bursts that would occur. And so you can see here, this is the number of simultaneous errors. That would have a spike. And the same spike would be very clearly visible on this chip to the right. So we had a paper that came out last year in March or so about gap engineering. So to show this, we built a sort of test chip that had a rectangle of qubits. 6 of these 12 qubits were gap engineered, and 6 of them were not. And that allows us to watch in real time as a high energy event comes in, and suddenly you can very viscerally tell which qubits are and are not sensitive to this high energy event, right? So right there, you can tell that these qubits aren't moving, and these ones are very, very sensitive. So this actually dramatically improves our performance against these events. And obviously, on our real chip, we put this gap engineering on all the qubits. And this removed that error floor that I just showed you earlier. There's another sort of sneaky error here that isn't represented in the sort of top-line numbers that are usually presented, fidelity and so on, which was leakage. So leakage is an error where your qubit leaves the nice 0-1 subspace that we always think about for a qubit and goes to some higher order event, a higher order state. And the issue with it is that it lasts for a while, and while it's lasting, anytime you interact with that qubit, you're going to pick up errors and phase errors and just noise in general. So reset means that this problem is kind of limited on our measure qubits, but data qubit leakage is really concerning because it just sits there and spits phase errors all over your device. So we developed this technique called data qubit leakage removal. This paper here discusses the specifics of how we did it. And essentially what it does is it uses a gate that is basically half our CZ operation. Our CZ operation applies a phase to the 1-1 state by traversing through 0-2. For leakage removal, we just do this operation once and take 0-2 to 1-1 and then reset the qubit. And this allows us to extract leakage and make it look like a computational basis error. This dramatically flattens out our detection event fractions. So in the previous experiment, the system would get noisier in later rounds, and that signature is basically removed in this current experiment. Sorry. And the thing I want to highlight here is that there are a number of these sort of rarer errors, if you want to think of it that way, that you don't notice when you're looking at sort of the general performance metrics of your system. But in error correction, you're incredibly sensitive to. And that's because you're removing a lot of the things that you understand well. And so fixing problems like this aren't represented in most of those top-line numbers, but are very important when trying to get error correction improvements, as we've seen here. So here this corresponds to a 35% increase in lambda, which again is that sort of factor of improvement you get as you increase in distance. And you can see pretty clearly here how the 3 and 5 without DQLR are much worse than 3 and 5 with DQLR here. Great. The last big difference between this experiment and the one from 2 years ago is that we did real-time decoding. So in the previous experiment, we ran the full 25 rounds or so, and then took that whole block of measurements and put it into a decoder, which is a piece of classical software that uses all of the measurements to infer what errors have occurred, and ran decoding, and then used that output to interpret the shot. But in a future like fault-tolerant quantum computer, this isn't a tenable solution. The reason is that you need to actually know what your logical measurements are in order to apply feed-forward, fatigue state injection, and all sorts of other applications. And so you need to actually be able to quickly know how to interpret your measurements, and you don't want that that time to scale with distance or scale with system length. So if you run 30 rounds, you better be keeping up with your system, with your chip. Otherwise, you're building up noise and you're building up time, and then at the end, you're going to have to wait a lot longer. And that's really the fundamental clock speed for a fault-tolerant quantum computer. So this slide is not going to be enough to explain the complexity of how we do this, but essentially, we build this decoding graph, and we have a buffer. We apply error correction, and we apply decoding in this sort of region, and then we kind of stream it through. In reality, we actually did save all the data sets here so we could release them, but in the future, one could imagine not even saving those data sets and having significantly cheaper memory costs as well. And you can see that latency does not go up with number of rounds or number of cycles, and here, this is the latency shown in a slightly different way, where this is distributions and this is just sort of error bars. Great, so now this sort of gives us a bit more reality to what we're presenting. This is the kind of decoding you would need to do in a actual fault-tolerant quantum computer to honestly compare against and project. Great. So lastly, I'm going to talk more about repetition codes. We again ran the same repetition code experiment we ran in 2023. And for the first while, it was going smoothly as we expected. Right? We broke through that error floor we showed previously, so the gap engineering helped. And now we're continuing on. We had a lambda of 8.4. Things were looking good. And then we found a new error floor. So it's now about 100,000 times smaller. That's good. But roughly once an hour, we have another sort of rare error burst that looks somewhat similar to the previous ones, but we can't understand yet. And we're ongoing sort of explorations of trying to diagnose what exactly it is and mitigate it for the future. But the nice thing about these experiments is that they really allow us to sort of look for like monsters hidden in the shadows that we haven't found yet. And this allows us to fix them, or start working on them at least, before surface codes could even dream of this level of performance. So in the past, repetition codes told us, hey, you got to fix these high energy events. And we were able to fix that in this current experiment where that's not a problem for us. So hopefully we're going to keep working on this problem and get it dealt with before we have any surface code experiments that are being impacted here. But at the 10 to the minus 10 level, like now you have to take an enormous number of shots to even see these error mechanisms. And that gives you a sense of the sort of rare events that we now need to be able to understand well to do error correction at the, at the next era that we're going into. With that, I believe I just have hopefully a conclusion slide, if I can get us there. All right. Oh, no. Sorry, no conclusions for you. Great. So, yeah, so here we just have a last plot of when these, to look forward to the future, when will these systems be ready. So on the x-axis here I have distance, so this is again like the size of the code we're using, and the y-axis is logical error rate. And you can see that for the previous 2022 result, we had a lambda of 1, and that corresponded to not seeing very much change. And now here we have a lambda of 2, and you're seeing slight improvements as we tick forward and forward. Our next milestone is to get to a 10 to the minus 6 logical error rate. This is the so-called mega-QoP regime that I believe Pascal talked about yesterday. And to get there, we really expect to need to improve on both axes. We're going to need to get better performing chips, so getting to these sharper and sharper slopes, while also building larger, right? To get good architecture performance, you need to improve in system quality and quantity, essentially. And this is sort of hopefully where we'll be in a few years, able to give a talk like this, in a future Q2B. And with that, I'm happy to take some questions.
Any questions?
The use cases we have? Yeah, so this is a single qubit, or like single logical qubit, right? So like the actual thing we're making here is equivalent to 1 qubit. And so there's not like a number of applications for a single qubit. The goal would be that once we get to this sort of mega-QoP regime, that's roughly where we expect to start seeing some interesting early fault tolerant toy examples at least. Maybe not business value, but at least, The random circuit sampling experiment that we talked about very recently is on the same chip, but yeah, so the same error parameters. The random circuit sampling paper that came out like a year ago, 8 months ago, on a 67 qubit chip, that was on a previous Sycamore architecture chip. So slightly worse parameters.
People can't hear you, sorry.
Yeah, thanks for the talk. Loud. Yeah, I'm curious of your opinion just of the quadratic scaling of the surface code and how you see this going into the future where, other approaches might require significantly fewer resources to reach the same distance but higher connectivity.
Yeah.
Clearly you guys are doubling down on like this planar architecture. Just curious on your opinion.
Yeah, so I think for us right now, we think that I think first of all, we should say that it's good to take smaller steps, and so we want to at least prove this out here. And a lot of these sort of LDPC architectures that I think you're sort of alluding to do have much better overheads. You have better encoding rates and so on, whereas the surface code is like rate 0, technically speaking. But we have been able to find ways to sort of reach similar overhead levels without having to leave our planar geometry. So there's a paper that actually Mike and Craig wrote on yoked surface codes, where you were able to sort of embed surface codes into a iceberg code, and that gets you a lot of the way towards some of these QLDPC architectures without having to leave the planar geometry. And that really simplifies, our lives on the experimental side, on the calibration side, as well as sort of right now in the research, progress side. It's good to have sort of a fixed point that we can, we know roughly we have the same resourcing in terms of connectivity and so on. We can just sort of work on building around it. But I think there's still a lot to find in terms of planar architectures. Whether we can get to full QLDPC overhead costs is a different question, of course.
I think we have time for one more. Okay. If not, let's thank our speaker again.